All right, so let's talk about Lab 1 report, which is for the density of water and the density of an unknown metal. So for page 1, I would like the lab report form that can be found in Canvas under the Files tab. The second thing that I would like for the next page is a graph. Most students will use Excel, but as long as it's computer generated, that's fine. And some of the components that you need are you need a title, you need an axis label. So for this one, the y-axis is going to be mass, and of course you need the units in grams. And then you also need a volume axis, which will be your y-axis. You need the label for that, as well as the units for that. And you're going to add in Excel or whatever else you're using in terms of computer generation, something called a trend line. And that will be a linear trend line, and you should get something that looks like y equals mx plus b. And the m value right here is actually your slope, which is rise over run, which will tell you what the density of water should be. So that m right there will give you the density of water from your graph. And that should be approximately 1 gram per mil. If it's not, then you've forgotten to subtract the mass of your empty beaker from the rest of your beaker plus water values. And I'll show that in a minute. For the next page, what I'm looking for is one set of representative calculations. So that means where you have volume final minus volume initial, where you've subtracted the mass of your beaker from the mass of the beaker plus water, where you show one representation of the density calculation as well as the average deviation. And then the last page, I would like data from the lab notebook. Please make sure that all of this is legible, meaning easy to read, and that you upload it as one document as a PDF in Canvas by the due time. So notice here, one of the things that you will have is you're going to go to your lab report form. So we'll start off with your lab report form. And the very first thing that you note is it says using data in table 1, calculate the values for water asked for in the table below. The calculated values in raw data are not the same thing. So what that means, I'm going to show you my data that I have, and here's the data that I have. And what that means is when we look at this table, the exact volume that we see here for 1 mil means that we have to go to our data table, and we're going to take our final value here and subtract from it the initial value. So I'm going to show that calculation. So I would have 1.06 mils. It happens to be that this particular student had it at exactly 0.00, and that means that that first value happens to be the same. So I would plug in that 1.06 into here, and I also have the correct sig figs. You should have 2 to the right of the decimal for volumes. Now when we talk about the mass of the top loading, we're going to go back here and notice that we have empty beaker for both top loading and analytical. So in order to deal with those, I've got to take 60.38, which is the mass of the beaker plus 1 mil, minus the mass of the empty beaker, 59.37. And when we subtract that, we end up with 1.01 grams. And you're going to do the same for the analytical balance, where you subtract the empty beaker from the beaker plus water. And you're going to keep doing that, where you take the empty beaker and subtract it from the next one, take the empty beaker, subtract it from the next one, and that's what you're going to plug in to that table. And you're going to continue that for the top loading and the analytical. And then of course you'll show me the density, where you're going to do density is equal to mass over volume. So you're just going to take your mass value and divide it by volume, and you should get approximately 1 gram per mil for each of these. And you're going to fill out this table. Then you're going to show me a representative calculation for the average here for the top loading density, the average here for the analytical density. And then notice here there's an average deviation, and in order to find that average deviation, we're going to go back to the procedure. And here in the procedure, notice that it's giving us the average deviation formula. And what you're going to do for that is you're going to take the sum of all 4 of those values, and x sub I means that you're going to take trial 1's density and subtract from it the average. You're going to take the absolute value of that, plus you're going to take x of trial 2, that means the actual density for trial 2, and you're going to subtract the average density overall, and then you're going to do that for 2 more. And when I say absolute value, that means you're going to make each of those values positive. You'll have 4 of them there, so you'll divide by 4, and that will go in as your average deviation. And average deviation tells us something about precision. It tells us how consistent or reproducible our values are. In order to have something that's accurate, you need a literature value. So we're going to go back here. It tells us to use the volume and mass data and of the top loading to create a graph. You're going to get the y equals mx plus b. Based on the graph, what's the average density? Remember, that's going to be the slope that you determine. And then it's got a couple of questions for you to ask. And then the last thing that it wants you to do, which is actually the second part of the lab, is it wants you to find the density of the unknown metal and then identify it. Now note, in the lab procedure, there is a table that limits the number or limits the actual number of unknowns. It's right here. And in fact, it notes also their densities, and there's a couple of them that are close. So if you end up in a situation here where you have a value that's close, think about the observations that you made in lab. For example, what did it look like? What color was it? Was it rosy colored in nature? Because if it was a rosy colored versus a silver color, then that should tell you whether it was copper or nickel when those values are close, and it could be one of those two. Just use both the data from the calculations as well as your observations to make a choice based off of what your unknown should be. Let's talk for a minute, though, about those calculations. So let's go back to the data from that one. Here I've set up a picture of what's going on. Here's my data that I have, mass of the empty flask. I've got the mass of the flask plus the metal. Then I've got the mass of the flask plus the metal plus the water. And then the last one is the mass of the flask and the water. Now notice what we are looking for is the density of the unknown. So that means we need the mass of the metal and we need the volume that the metal took up. So we need to know what this is right here for the volume part, because I'm going to label this a little bit. So those little circles, we're going to assume that's the metal. And above that metal is the water that you put in there. And then over here, I have the water filling up the whole flask. And so we're going to use this information that you used from lab in order to figure out the density of the unknown metal. Now, the first thing is you've got a mass here of the metal. That should be relatively straightforward because you're going to look up here and notice you have the mass of the empty flask and the mass of the flask plus the metal. So you're going to subtract the mass of the empty flask from the mass of the flask and the metal, and that will give you the mass of your metal. So that right off the bat gives us one piece. What's a little more difficult though is actually finding the volume of the metal. So when we look at that, we have to look at two pieces. We have to look at what is the actual volume that the water ends up filling in the flask. And then we have to look at how much volume is there to the water filling it above the metal. And if we subtract those two, if we can find out what they are, then that's going to give us the volume of the metal. So to find that, we're going to use the density of the water from our graph that we generated via computer. For me, that was in Excel. And I found out just to make it simpler, I'm going to say that the density of the water of my graph was 1. And then we've got to figure out what's the mass of water that filled the whole flask. So when I come up here, I'm going to look at this and notice here, I've got the mass of the flask plus the water. So I'm going to take that 65.79 and I'm going to subtract from it the 33.15, which is the mass of my empty flask, in order to find out what the volume of water is. So I'll find a numerical value for the water of volume, or volume of the water for that, and that'll be in mils. And then the second part of this, so I'll go to a different color, is now I've got to find what is the mass of water above the metal. So in this last step where we're finding the mass of the water above the metal, we've got to go back to our data up here and notice we've got the mass of the flask plus the metal plus the water at 97.27 grams. And then we've got the mass of the flask plus the metal. So we're going to use those two pieces to find out what is the actual mass of that water above the metal. So we're going to start with that, and we're going to take 1 as the density of water from my graph. You're of course going to use whatever's from your graph. And then we're going to take this mass right here, that is the mass of the flask plus the metal plus the water, 97.27, and subtract from that the mass of the flask plus the metal, which is 68.75. And that's going to leave us with the volume of the water above, and I'm just going to do METAL really small. And so we can solve that. And when we solve that, it should be less than the volume of the water. Then we can take these numbers. Here's the volume of the water. We'll plug that in right there. And we'll take the volume of the water above the metal and we'll plug it in there. And that will get us to the volume of the metal. And that volume of the metal will then go in right here. And then lo and behold, from that, we'll end up with the density of the unknown metal.